Today, let's solve my first triple improper integral. Let's have a look. We are all going from negative infinity to positive infinity, and then we have this thing, and then dx, dy, dz. How do we solve this? This right here should remind you of the classic way of solving the Gaussian integral, right? Where you just take this, multiply by itself. The first one is in terms of x, the second one is in terms of y, and you produce a double integral, and then you change the rectangular coordinates to polar coordinates. But that's only 2 dimensions. Here we have 3 variables, so we are in the 3D world. Polar is not enough. We need spherical coordinates. And let me review that with you guys real quick. We need rho, theta, and phi. Firstly, when we are in the rectangular world, in the 3-dimension situation, is that we're trying to get to a point in a space. You will have to tell me how far to go left and right, forward and backwards, and then up and down. For the spherical, we need rho, theta, and phi, and this is how to think about it. Let's imagine I have a fly over there, and by default, I'm facing this direction, and I'm going to be holding a laser gun right here. I'm trying to get rid of the fly, right? Pointing like this. So first, I will have to do a rotation, and the rotation is my body rotation. So it's like this. And that rotation is the angle theta. And once I can see the fly in front of me, I'm going to aim to the fly. I will have to do this. That's a second rotation. And that's the angle phi. And once I can aim the fly, I will shoot my laser right from where I am to the fly so I can get rid of the fly. And that distance is rho. And that's the idea. By the way, I just want to mention that for math, we write rho, theta, and phi. And I think for physics, sometimes they switch this and that. So it just depends on the convention. And I do have a detailed explanation going over how to change from rectangular to cylindrical and also spherical, all that. So I will have the links in the description for you. So right now, I will just tell you guys the formulas that we need. When we have x squared plus y squared plus z squared, that will give us rho squared. And that's actually just directly from the Pythagorean theorem or the distance formula in the 3D. And then next, we also have to know this right here. dx, dy, dz. Remember when we have dx, dy changed into polar, we need r, dr, d theta. The r can be derived from the Jacobian, or you can do geometry. Right here, we actually need rho squared times sine phi. And again, you can do Jacobian or do geometry. And yes, I do have videos on them already. The links will be in the description for you to take a look. And then I'm just going to do d rho, d theta, d phi. With all that, let's go ahead and go to the spherical world. I still have a triple integral. Inside here, we get square root. All this is just r squared. And then e to the negative, all that is, again, r squared. And then lastly, all this is all that. So rho squared sine phi, and then d rho, d theta, d phi. Not done yet, because we still have to figure out the boundary right here. Starting with the rho. Remember, rho is the distance from the origin to whichever the point is in the space. And because these right here are going from negative infinity to positive infinity, we are covering the entire space. So for rho, we better have from 0 to infinity. So I can get to anywhere, right, the distance. Next, for the theta, well, to cover everything, I have to rotate one loop, right, because of the chord. But anyways, 0 to 2 pi. Lastly, the phi is this rotation. 0 to pi only. Do not go from 0 to 2 pi, otherwise you'll be double counting. It's just 0 to pi. Alright? So if you rotate like this one loop, and then you do this, and then you just have the distance from 0 to infinity, you cover the whole space as well. So that's the idea. And now this is very nice because we can simplify this a little bit. You can see that row, right? You can see that all this right here, they have row, and I'm just going to bring them together into one integral. So let's take a look. Integral going from 0 to infinity. This right here is just row. Of course, cancel this, it's just row. Along with row square, we get row to the third power. And then we have e to the negative row square, and that's in the row world. Next, I'm going to put down theta, which is just going from 0 to 2 pi d theta. Technically it's a 1, but it doesn't matter. Lastly, don't forget we have the sine phi as well. For the phi, we go from 0 to pi, and then we have sine phi and then d phi. And the beauty of this is that we just have to work this out, work that out, and then multiply the results. That's it. For this, we will have to do some integration by parts. So I'll do it on the side real quick. Remember, integration by parts means you break the integral into two parts. One part is to be differentiated, the other part is to be integrated. I'm going to, because of the negative row square, I'm going to have p row times, I'm going to have row times e to the negative row square, because I can integrate this with u sub. And then I will be differentiating the rest, which is row square. This times this, we get that. Okay, if you let u equal negative row square, you need to have negative 2 right here, right, to get the du. Well, if you have negative 2, you will have to divide it by negative 2. So you get negative 1 over 2, and then you get e to the negative row square. Now, differentiate this, you get 2 row. Okay, and then this times this is the first part of the answer. I'm going to work out this integral right here. So we get negative 1/2 row e to the, well, row square, e to the negative row square as well. This one has no integral, right? When you do this times that. Then I'm going to multiply these two things in this row, and then put that inside of integral. Negative times negative, so it's going to be a plus integral. 2 and 2 cancel, so we just have row, and then e to the negative row square. And for this, we can just do u sub again. So it's pretty much the same one right here. So again, you need to multiply by negative 2 and divide it by negative 2. So all that, we get negative 1/2, and then it's just e to the negative row square, along with this right here. Now, this right here is the result. After we integrate that, we will have to go from 0 to infinity. Here's the beauty. When we put infinity into this part, notice that we have an exponential part. That, when it goes to the bottom, on the top is what? A polynomial, row square. That is going to be a smaller infinity compared to the e to the negative infinity. So we will get 0. And you can use L'Hopital's rule, do some limit business, you get 0, alright? And then when you plug in infinity into here, again, take the limit because of the e to the negative infinity, that's also 0. And then when you plug in 0 into here, thanks to the row square, that's 0. When you plug in 0 into here, that's going to be e to the negative 0, which is 1, and you have negative 1/2. But it will be a minus negative 1/2. So all in all, this part is going to be positive 1/2. Okay? Then, for this part, you get 2 pi. And then for this part, when you integrate sine, you get negative cosine. And then when you plug in pi, you get negative 1, because cosine of pi is negative 1. So you get positive 1. Minus negative cosine of 0. So it becomes minus 1, becomes plus 1. So 1 plus 1 is 2. Now, ladies and gentlemen, cancel this and that. Final answer, we get 2 pi. And that is my first triple improper integral. That's it.